everyone, I hope all of you are doing good and I am here with a video series on class 10 maths real numbers. Yes, so this is the time when we are going to start our class 10 maths with a bang. And the first lesson that we are going to learn is real numbers. As always, we'll focus on the concepts and we will also focus equally on the questions, because the more questions we solve, the better our concept is. So we are going to divide this entire lesson of real numbers into two parts. In the first part, that is in this part, we are going to learn about Euclid's division lemma, and in the next part, we are going to learn about the fundamental arithmetic theorem. Both are equally important, so I would request you to watch both the parts completely, and after that, you will be self-dependent to solve all the questions from this lesson. So before we actually move ahead with the lesson, we need to do a very quick recap. Recap of what? Recap of the numbers, the types of numbers. So numbers are broadly categorized into two types, real numbers and imaginary numbers. You must be thinking, imaginary numbers? What are they? I haven't heard of them before. Are they imaginary? Do they not exist in real? Well, you can identify imaginary numbers by seeing how they look. So basically, they have a real number component like a 2, 3, 4, 5 or 6. But along with that, they have an I, which is also called iota or the imaginary unit. So they are imaginary numbers like 2i, 4i, 5i and so on. Imaginary numbers are also called complex numbers, and yes, they are a little more complex than the real numbers, and that is why we are not going to study about them right now. So we will learn about complex numbers in higher classes. For now, we will be within the limits of real numbers. So let's focus on real numbers. So real numbers can be classified into two categories, rational numbers and irrational numbers. What are rational numbers? Numbers in the form of p by q, where q is not equal to 0 and they are integers. So they are rational numbers like 1 by 2, 2 by 3, 2, 5, all rational numbers. Then what are irrational numbers? Exactly the opposite of rational numbers. They cannot be represented in the form of p by q. So examples of irrational numbers would be root over 2, root over 5, root over 6. So they are all irrational numbers. Now, let's focus on rational numbers. So inside rational numbers, we have integers. What are integers? So integers include all the positive numbers, all the negative numbers and 0. That is plus 1, plus 2, plus 3, plus 4. Again minus 1, minus 2, minus 3, minus 4, so on, and 0. So all of these together are integers, and integers do not include the decimals. So integers are basically those numbers which are seen on a number line. You remember the number line? Good. Next comes the whole numbers. Whole numbers are those which starts from 0 till infinity. The next is natural numbers, which starts from 1 and goes till infinity. So you see, I am gradually coming down, as in I can say that the natural numbers are a subset of the whole numbers are a subset of the integers are a subset of the rational numbers are a subset of the real numbers. It's nice, right? Okay. So that's about the numbers. Now, I still want to go one step ahead. Now, even within the whole numbers, we have two categories, that is prime numbers and composite numbers. So what are prime numbers? Those numbers which have only two factors, 1 and itself. That means those numbers are not divisible by any other number except itself and 1. For example, 2. 2 is divisible. You can only write 2 as 2 into 1 or 1 into 2. It is not divisible by any other number. Similarly, 5. You can write 5 either as 1 into 5 or 5 into 1, but no other number is a factor of 5. On the other hand, if you look at 6, you can write 6 as 1 into 6, 6 into 1, but you can also write it as 2 into 3 or 3 into 2. Right? So that means 6 has 4 factors, 1, 2, 3 and 6. So numbers like 6 are called composite numbers. So composite numbers means they have many factors. Prime numbers means they have just two factors, 1 and itself. Cool. So I think now we are thorough with all the types of numbers, and I feel that we are ready to start with Euclid's division lemma. So what's Euclid's division lemma? Now again, the first thing that strikes our mind is, what is this lemma? Haven't heard of it before. We have heard of theorems, we have heard of laws and rules, but what's lemma? So lemma is basically a proven statement that is used to prove another statement. So it's like you have a statement, you use it just to prove something else. In fact, Euclid's division lemma was known for several years. So it was into existence for a very long time. But then after quite a few years, from this division lemma came up the division algorithm, which is called Euclid's division algorithm. Now you will ask, what is algorithm? So algorithm basically is a series of steps that we need to follow to solve a particular type of problem. So it actually tells you the steps. Okay, this is step 1, step 2, step 3, step 4, and you need to follow these steps and you will be able to solve a problem. Now, what kind of problem? So at least in this video, what you will see is we will be trying to find out HCF of two numbers, that is highest common factor. HCF you all know, right? You have learnt about it in junior classes. But what we will do differently in this video is we will learn how to find HCF of two numbers using the Euclid's division algorithm. Clear? Now the Euclid's division lemma and the algorithm, they are so closely connected because the algorithm came from the division lemma. They are so closely connected that we often refer them as the division algorithm only, right? So I think we understood what's lemma and what's algorithm. So Euclid's division lemma states that if we are given two positive integers a and b, then they can always be written as a is equal to bq plus r, where r is greater than or equal to 0 and less than b. And you will see very soon that how this division lemma was used to make the Euclid's division algorithm. Our problem statement basically is to find HCF of two positive integers. So that's our problem statement. So we will assume that those two integers are c and d, and we will write them in this form. C is equal to dq plus r, where r is greater than or equal to 0 and less than d. Okay, let us do one thing. Let us take an example and try understanding along with the example. So that will make our task easy. So let us suppose that you are given a problem statement that you will have to find out the HCF of these two numbers, 455 and 42. HCF is highest common factor, right? Now let us assume that this is C and this is D. So let us write it in this form. So C is equal to D into something. What is that something? How will we know that? So we basically need to divide 455 by 42. So that ways we will know what is the quotient. So this is 35, right? So in this case, 42 into 10 plus 35. So in this pattern, we can write this. Correct? So here we see that R is less than D. That means R is less than 42. 35 is less than 42. So we have successfully written it in this pattern. So that's my step 1. Now step 2 tells us that if R is equal to 0, then D is the HCF of C and D. But that is not the case with us, right? So R is not equal to 0. Right now R is 35. And if R is not equal to 0, apply the division lemma to D and R. So which is my D? So D is 42 and R is 35. So now we have to apply the same division lemma to 42 and 35. So 42 is equal to 35 into what? Plus how much? So 35 into 1 is 35 and then the remainder will be 7. Correct? So even now also the remainder is not 0. So we again need to apply the division lemma between D and R. That means between 35 and 7. So therefore this will be 35 is equal to 7 into, so 7 5s are 35. So this time the remainder is 0. Now the moment the remainder is 0, then D becomes the HCF. D, that is, what is D in this case? So in this case 7 is D. So therefore HCF of these two numbers will be equal to 7. So you understand, right? Basically we need to apply the Euclid's division lemma in this fashion. As long as you do not get remainder is equal to 0, you need to continue applying this division lemma to D and R. That's it. So this is how we do it. So finally, as I said, we continue the process till the remainder is 0. The divisor at this stage will be the required HCF, as you saw here. So we continued it for 3 steps and finally 7 became the HCF. Let us try a few questions. Question number 1. Use Euclid's algorithm to find the HCF of 4052 and 12576. Okay, so let's write it in the same form. C is equal to DQ plus R. So let us say C is 12576 is equal to DQ, that is 4052 into how much? So again you need to divide this with this to find out the quotient and remainder. So the quotient is 3 and the remainder is 420. So the remainder is not 0, so we will apply it to D and R. So the second step will be 4052 is equal to 420 into 9 plus 272, and you will see with each step the value of remainder is decreasing, right? So again not equal to 0. So we will apply it to D and R, that is 420 and 272. So this is 272 into 1 plus 148. Again not equal to 0. Therefore D and R, we will apply the same lemma. So this would become 272 is equal to 148 into 1 plus 124. Again not 0. So again we'll apply to these two. So 148 will be equal to 124 into 1 plus 24. Not equal to 0 again. So 24 and 124. So this becomes 124 is equal to 24 into 5 plus 4. Again not equal to 0, but now it seems that we are closed, because you see we started with 420 as remainder and now we have reached to 4. So now we will apply it between D and R, that is 24 and 4. So 24 is equal to 4 into 6 plus 0. So finally the remainder is 0 and the value of D here is 4. So that means HCF of these two numbers is 4. So this is how you are supposed to do it. So I did it very quickly, but how do you find these values? Just by multiplying this number by this number. So that's how you find it. Question number 2. Show that any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5 where q is an integer. Okay. So let us assume that a is any positive integer. And let us suppose b is another integer. In fact, in this case, let us suppose that b is 6. Why 6? Because if you look at the form that we have to prove, they all have 6. So let us assume that b is 6. In some time you will get to know why we assumed b to be 6. Now we will apply Euclid's division lemma. So we learned that Euclid's division lemma says that C is equal to DQ plus R. So here C and D are replaced with A and B. So A is equal to BQ plus R. So let's put that. So this becomes A is equal to 6Q plus R. And what is the value of R? R is greater than equal to 0 and less than 6 because B is 6. So therefore, the possible values of R will be 0, 1, 2, 3, 4 and 5. Correct? Now, let us put these values of R. Then what are the possible values of A? If R is equal to 0, A will be 6Q. Other possible value could be 6Q plus 1. Other possible value could be 6Q plus 2. Other possibility 6Q plus 3, 6Q plus 4 and 6Q plus 5. So these are the possible values of A for different values of R. This can be written as, now by looking at all these options, you can very quickly identify that which of these are even and which of these are odd. Even as in it should be divisible by 2. So looking at this, you can see that this is divisible by 2, right? Because 6 is divisible by 2. This can be written as 2 into 3Q. This can be written as 2 into 3q plus 1. This can be written as 2 into 3q plus 2. So we see that all of these are divisible by 2 and therefore these are the even options. But here we are looking for the odd options. So the odd options would be 6q plus 1, 6q plus 3 or 6q plus 5. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So the situation is somewhat like this, that we have a band in front which has 32 members, and then behind them we have a group of 616 members who would march behind the band. Now, how will these guys stand? So they would stand like this. Now, we have to identify in how many columns. Now, the question says that the number of columns should be the same, as in, let's say if there are 8 people standing here, so here also there should be 8 people, so that it is symmetrical. So the number of columns need to be the same. That means here also if it is 8, here also it has to be 8. Here also if it is 16, here also it has to be 16. Okay. So now we have to find out what is the maximum number of columns in which they can march. Now, whatever is the number of columns here for the band, that number has to be a factor of 32, right? Because 32 people need to stand. So it could either be like in 2 columns, where 16 in each, 16 in one, 16 in another. It could be in 4 columns, 8 in each column, right? So that number has to be a factor of 32. Similarly, the number of columns here should be such that it is a factor of 616. Now the question says that the number of columns has to be same for both of these groups. That means this has to be a common factor of 616 and 32. The question also says that we need to find out the maximum number of columns. That means this common factor also has to be the highest value. So that means what we are looking for is the highest common factor of 616 and 32. That is what we need to calculate. So the trickiest part of this question was to understand and interpret the question, that what exactly do we need to find, right? Now once you know that, I think it's pretty easy to find out the HCF. So we can follow the division method. So let us divide 616 by 32. So 32 ones are 32. Then we have 29. And here we get 296. So 9s are 288. Then we have 8. Now with this 8, we again divide 32. So 8 4s are 32. And that's it. So we get HCF as 8. Now since the HCF is 8, that means 8 has to be the number of columns in which they can march. Question number 4. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Okay. Now let us assume that a is any positive integer. Let us assume that positive integer is a. Okay, now as per Euclid's division lemma, we can write a is equal to bq plus r, where r is less than b and greater than equal to 0. Now in this case, let us assume that the value of b is 3, again for the same reason, because look at the form in which we have to prove it. So this becomes 3q plus r, therefore the possible values of r would be 0, 1 and 2. Now let's put these values and see what are the possible options that we get for a. So one possible option could be 3q, the other option could be 3q plus 1 and the other option could be 3q plus 2, right? So now here we are looking for square of any positive integer. So basically we are looking for a square. So that would become 9q square. This would become 3q plus 1 whole square. And this would become 3q plus 2 whole square. So this becomes 9q square. This becomes a square plus 2ab plus b square. And this becomes a square plus 2ab plus b square. Now let us see if we can write it in the form of 3m or 3m plus 1. So this can be written as 3 into 3q square. This can be written as 3 into 3q square plus 2q plus 1. This can be written as 3 into 3q square plus 4q plus 1 plus 1. Now let us assume that this is some constant m. Similarly, let us assume that this is some constant m or m1, and this is some constant, say m2. So this can be written as 3m, this can be written as 3m1 plus 1, this can be written as 3m2 plus 1. But if you look at the form is either 3m or 3m plus 1. Those are the two forms in which we can write the square of any positive integer. And that's what we had to prove. Now let's look at question number 5. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. So it is a question of the very similar pattern. Right, again let us assume that this any positive integer is a, and this time let us assume that the value of b is again 3. Why? Because here we will be dealing with cube, right? So you will understand it for yourself. So a is equal to bq plus r. So possible values of r would be 0, 1 and 2. So let's put those values. So we would get a is equal to 3q, or a is equal to 3q plus 1, or a is equal to 3q plus 2. Now in the first case, what's the value of a cube? We get 27q cube, which can be written as 9 into 3q cube, which is in the 9m form. Now let us look at the second case. So in the second case, if we calculate a cube, this becomes a plus b whole cube. Now let's put the formula so that it becomes a cube plus b cube plus 3ab a plus b, right? So this becomes 27q cube, 27q square plus 9q plus 1. So this can be further written as 9 into 3q square plus 3q cube plus 3q square plus q plus 1. So this is of the form 9m plus 1. Similarly, if we look at the third situation, we see that a cube is equal to 3q plus 2 whole cube. That is equal to a cube plus 3ab into a plus b cube. So this is equal to 54q square plus 36q plus 8. So this can further be written as 9 into 3q cube plus 6q square plus 4q plus 8. So this again has been written in the form of 9m plus 8. So we see that a cube of any positive integer can be written in one of these forms. I hope you found the video useful, and with this video your concept of Euclid's division lemma must be crystal clear. But I would still advise you to practice a few questions on this topic and then move on to the next video. In the next video we are going to learn about the fundamental theorem of arithmetic. So stay tuned.